I'm going to quickly go over sine, cosine, tangent ratios. So if we have a right angle triangle with the angle theta directly opposite, we label this opposite. This is the hypotenuse. And this is the adjacent. So those are the sides of the triangle. So students usually remember these ratios using so, ca, toa. So for sine theta, it's opposite over hypotenuse. Cosine theta, it's adjacent over hypotenuse. And for tan theta, it's opposite over adjacent. Let's have a look at the reciprocal functions. So the cosecant function, which we write as cos CSC theta, that's the reciprocal of sine, so it becomes h over o, hypotenuse over opposite. The secant function we write as SEC theta, that's the reciprocal of cosine, so that becomes h hypotenuse over adjacent. And then the cotangent function, which we write as cot theta, and that's the reciprocal of tangent, so this becomes adjacent over opposite. As well as this, we've got cosecant theta, again is the reciprocal of what? So it's 1 over sine theta. Sec theta, reciprocal of cosine, so that's 1 over cos theta. And cotangent theta, reciprocal of tangent theta, so it's 1 over tan theta. Also, cotangent theta equals cos theta over sine theta. Tan theta is sine theta over cos theta. And cot theta, 1 over sine theta cos theta. Let's have a look at these reciprocals again and see an alternative way of writing them. So we can have sine x cos x equals 1. Cos x sec x equals 1. That should be sine x cosec xksc. So that's the reciprocal. Cos x sec x equals 1. And tan x cot x equals 1. and then factors that are reversed, if we look at those. Say we have sine theta minus 1 over 1 minus sine theta. This equals minus 1. If we have something like 3 minus cosec theta over cosec theta minus 3, so these are reversed on top of each other, that equals minus 1. And then last but not least, we have sine theta equals cos, if it's in radians, pi over 2 minus theta equals 1 over cosec theta. This can be regarded also as 90 minus theta. So similarly, cos theta equals sine pi over 2 minus theta equals 1 over sec theta. Tan theta equals sine theta over cos theta, which equals cotangent pi over 2 minus theta equals 1 over cot theta. Cot theta equals cos theta over sine theta, which equals tan pi over 2 minus theta, this is in radians, equals 1 over tan theta. And then sec theta, that equals cosec pi over 2 minus theta equals 1 over cosec, 1 over cos. And then cosec theta, let's push this up a little bit, cosec theta equals sec pi over 2 minus theta equals 1 over sine theta. It's quite easy to think that the cos is related to the cosec because it begins with a C, but the important thing to remember here that it's not. Cosec theta is 1 over sine theta, sec theta is 1 over cos theta. One way of remembering the trig functions is to use a hexagon. We label it sine, cos, tan, cot, sec and cosec on the vertices with a 1 in the middle. So when we go round clockwise, starting at sine, say in this direction, so we're going to go that direction. So we have the quotient identities. So if we start at tan and we're going round, tan equals sine over cos, sine equals cos over cotangent, and cos equals cotangent divided by cosecant. If we go, again, let's label them sine, cos, tan, cot, sec, cosec. If we go in this direction, say one arrow here and one arrow here, or we go in this direction, that way and that way, that way and that way, we get the product identities. And this is, so tan x, cos x is sine x, tan x, cot x is 1, there should be 1 in the middle, and tan x cosec x equals sec x. To go again, sine, cos, tan, cotangent, sec, cosec. This time if we go diagonally, this way, there's one there, we get the reciprocal identities. So this is sine x is 1 over cosecant x, cos x is 1 over sec x. So if you can't remember them, you can use this little method using the hexagon. If we want to know complementary angles, so again we have sine, cos, tan, cotangent, secant, cosecant. So the complementary angles go across like this, across like this, and across like that. So sine x is cos 90 minus x, tan x is cotangent 90 degrees minus x, and secant of x is cosecant 90 minus x. For example, in this complementary thing, sine of 30 degrees equals the cos of 60 degrees. Here we have, if we want to learn the Pythagorean identities, we again put the 1 in the middle, sine, cos, tan, cot, sec, and cosec. This time we go around and down like this, around and down like this, and around and down like this with the arrows. So we just follow the arrows and we get sine squared x plus cos squared x equals the 1, which is in the middle here. Going around here, 1 plus cotangent squared x equals cosec x. And then finally here, tan squared x plus the 1 equals sec squared x. So let's have a quick look at sine, cosine and tangent of some common angles that are used in trigonometry. So we're going to have a look at the sine, cosine and tangent of 60 degrees, 45 degrees and 30-degree triangles, right angle triangles. So if we have an equilateral triangle and we divide it into two, this being a right angle, this is 60 degrees, this is 60. When we divide it into two, this becomes 30, and this is 60 degrees. Each side is a unit, so that would be 1. 1 being an equilateral triangle. When we divide it into two, this 1 divided exactly into 2 becomes a half. This hypotenuse remains 1. This is 30 degrees, and we need to find x. So using Pythagoras, we get a half squared plus x squared equals 1 squared. So a quarter plus x squared equals 1, x squared equals 3/4, and so therefore x is square root of 3 over square root of 4. This is the cosine of 30 degrees. If we want the sine of 30 degrees, we have sine is opposite over hypotenuse. So now we know that this is square root of 3/2. So the sine would be the opposite, which is half, divided by the hypotenuse, which is 1, which would leave us with a half. So that's the sine of 30 degrees. If we want the tangent of 30 degrees, the tangent is the opposite over the adjacent. So the opposite was 1 and the adjacent was square root of 3/2, and this would leave us with, when we get rid of the square root, so let's do that. So that would be half, sorry, the opposite was half. So there. So that would be a half times 2 over square root of 3, which equals 2 over 2 square root of 3. Now to get rid of this square root of 3, we rationalise the denominator. So that's multiplied by square root of 3 over square root of 3. And we're left with we can take out those and we're left with 1 square root of 3. Rationalise the denominator now, and we're left with square root of 3 over 3. And that is the tan of 30 degrees. Sine of 60 degrees, if we look at this triangle, is the opposite over the hypotenuse. So this would then be, the opposite is square root of 3 over 2 divided by 1, which would just be square root of 3 over 2. Cosine of 60 degrees would be the adjacent over the hypotenuse. So the adjacent to 60 degrees is a half and the hypotenuse is 1, so that would remain a half. The tangent of 60 degrees, that would be square root of 3 over 2 divided by half. This is then square root of 3 over 2 times 2 over 1, which is 2, square root of 3 over 2, which is square root of 3. So tan of 60 is square root of 3. Now let's have a look at 45 degrees, a right angle triangle. Let's move this up a little bit so you can see. So, right angle triangle, 45 degrees, 45 degrees, and x. So from Pythagoras, x is the square root of 2. So sine of 45 degrees is 1 over square root of 2, and when we rationalise the denominator we get square root of 2 over 2. Cos 45 degrees is again 1 over square root of 2, and that again is square root of 2 over 2. Tan 45 degrees is square root of 2 over 2, which is a sine, divided by the cosine, which is square root of 2 over 2, and that's 1. So those are the most common angles. When we're talking about trigonometric functions and trig ratios, the unit circle is used to work out the value of sines and cosines for the common angles 30 degrees, 45 degrees, 60 degrees and multiples thereof. The unit circle consists of, if we draw a circle on the xy plane, so this is the x and this is the y, and then this would be 1, 1, minus 1, minus 1. So the xy coordinates here would be 1, 0, xy would be 0, 1, minus 1, 0, and 0, minus 1. And we have the unit circle which is divided into 4 quadrants. So this would be quadrant 1, quadrant 2, quadrant 3 and quadrant 4. Then what we need to consider is the cast, C-A-S-T. C stands for cosine, A stands for all, S stands for sine, and T for tangent. So this is, the fourth quadrant is C, the first quadrant is A, second quadrant S, and T. And what we find is that in quadrant 1, it's A, which is all positive. So the signs of cosine, sine and tangent are all positive. In quadrant 2, only sine is positive. Quadrant 3, tangent only is positive. And in quadrant 4, cosine only is positive. If we think about it and our projections onto the xy axis, when we're in quadrant 1 and we're projecting, say, an angle here and here, both sine, which is here, and cosine, which is along the x-axis, are positive. In quadrant 2, only the sine, which is on the projected onto the y-axis, is positive. Cosine, which would be along here, along the y-axis, is negative. So quadrant 1 all positive, quadrant 2 sine only positive, quadrant 3 tangent only positive, and quadrant 4 cosine only positive. Sometimes confusion about the unit circle and radians. So if we consider like 360 degrees is 2 pi radians. So therefore, when we're looking at here, here, and here, and here, so this is a 0, 0 point. So at 90 degrees, which is here, this would be pi over 2 radians. At 180 degrees, which is here, we have pi radians. And at 270 degrees, we have 3 pi over 2. And here, when we're back to 360 degrees, we have, because it's a unit circle with a radius of 1, we have 2 pi radians. So this would be 2 pi. Then what we do is we split our circle into 30 degrees. This would be 45 degrees, and this one 60 degrees. Now from these calculations again, we get 30 degrees is pi over 6, 60 degrees is pi over 3, and 45 degrees pi over 4. So let's label those. So 30 degrees would be pi over 6. 45 degrees would be pi over 4. And 60 degrees would be pi over 3. So now all we need to do is go up in multiples of, for the 45 degree lines, which is here, here and here, we need to go up in multiples of pi over 4. So we have pi over 4, then we have 3 pi over 4, 5 pi over 4, and 7 pi over 4. Then for every other angle, that's this one, all the other angles which are multiples of 30 degrees, we need to go, 30 degrees was pi over 6, so we need to go up in multiples, and so this then becomes pi over 6, this is 2 pi over 6, which when we cancel down becomes pi over 3. So this one then becomes 4 pi over 6, which when, so let's write that here, 4 pi over 6. When we cancel that down, that becomes 2 pi over 3, and similarly we get 5 pi over 6. This is 6 pi over 6, which when we cancel becomes pi. 7 pi over 6, 8 pi over 6, which when we cancel it down becomes 4 pi over 3. This is 5 pi over 3, and this is 11 pi over 6. And that's how we label it in radians. So first of all we go up multiples of pi over 4, and then multiples of pi over 6. I'm just going to go over how to remember the unit circle and the values of sine and cosine. So let's have, so x and y. The x is the cosine and the y is the sine. X and y, and this is unit circle, so this is 1, 1. So we previously worked out from using triangles and the equilateral triangle with sides of 1 and triangle with 45 degrees with sides of 1 for the shorter sides, the sine and the cosine. So if we want to quickly remember those, how do we do that? Well, this is 30 degrees, this is 45 degrees, and this 60 degrees. Pi over 6, as we previously said, pi over 4, and pi over 3. So how to quickly remember the values of the cosine and the sine? We write 1, 2, 3 downwards, and then 3, 2, 1. As a fraction over 2, the comma, and then square root the tops. And those are our values. square root of 1 and square root of 1 remain as 1, so we can just essentially consider that as half and that as half. Very important concept when we're talking about trigonometric functions and sine and cosine in particular. I like to think of sine and cosine as projections onto the x and y axis. So if we have this as the y axis and this as the x axis, and this is, say, theta, 30 degrees, we have a point here, and if we project this line onto the y-axis, this is the sine. So this projection would be the sine, which is a half. For the cosine, we project down onto the x-axis, so this would be the cosine, and for 30 degrees this is the square root of 3 over 2. So this is cosine. So this is the sine, and this is cosine. When we write our coordinates x and y, so x then becomes cosine and y becomes the sine. Okay, let's go over how to complete the full unit circle. So as we said before, we do 1, 2, 3, and then the opposite way around, 3, 2, 1, all over 2, and then square root at the top, so square root of 3 over 2, square root of 2 over 2, square root of 2 over 2, square root of 3 over 2. Now to get into quadrant 2, the values we just flip across, so this one comes over here, these values, so that's a half square root of 3 over 2, square root of 2, square root of 2 over 2, and then square root of 3 over 2 and a half. To get quadrant 3, we flip this over, so this value comes to where 7 pi over 6 is, so that's square root of 3 a half, square root of 2 over 2 twice, and then a half square root of 3 over 2. For quadrant 4, we flip this across, so this value here, the 30 degrees, would come where 11 pi over 6 is, so that would be square root of 3 over 2 a half, square root of 2 over 2, square root of 2 over 2, and then a half square root of 3 over 2. Now we mustn't forget our cast, so this is C, A, S, T. Quadrant 1, all are positive. Quadrant 2, only S, which is sine, is positive. So sine is the y coordinate, so that's put a minus on the half, leave that positive. So the cosine is negative. On quadrant 3, only the tangent is positive, so both these are negative. and on quadrant 4 only cosine is positives, so only the first one is positive, so the sign is negative. So negative, negative, negative. And that's your unit circle completed. Okay, let's look at trigonometric functions and finding exact values. So if we remember from our unit circle, we can do quickly 1, 2, 3, and then 3, 2, 1, over 2, over 2, square root, that would be our 30, 45, 60 degrees. Also, we have to bear in mind our cast quadrants, C-A-S-T. So in quadrant 4, only the cosine is positive, all positive in quadrant 1, only sine positive in quadrant 2, and only tangent positive in quadrant 3. So this means that if we have the cos of, say, 170 degrees, which would be in quadrant 2, it would be positive. If we have the tangent of 300 degrees, it would be in quadrant 4, so it would be negative. If we have the sine of 150 degrees, it would be positive. 170 degrees cos would be negative because only sine is positive in that quadrant. Okay, so if we were asked for the sine of 150 degrees, an exact value, this would be 180 degrees minus 30 degrees. So what we try to do is draw a little diagram with our 4 quadrants in, and then try to make our angle an acute angle. So 180, so this would be 0, 180 minus 30 would be here, so this would be our 30 degrees. And then the sine of 30 is a half. If we have the cosine of 210 degrees, this would be 180 plus 30. So if we have our little quadrant diagram, draw a quadrant diagram. This is 0 degrees. We always try to draw an acute angle from the horizontal. So 180 plus 30 would be here, 30 degrees. And then in quadrant 3, cosine is negative, so our cosine 210 degrees would be the same as cos pi plus 30 degrees, and that would equal negative square root of 3 over 2. In evaluating trig functions, if we have cos pi over 3, which equals 60 degrees, we go clockwise around our quadrant diagram, and the cos of 60 degrees is a half. Cos of minus pi over 3 is 60 degrees in the anti-clockwise direction, which would equal 300 degrees, and that is still a half. Because the minus and the plus give us the same trig ratio, this is called an even function. If we consider sine pi over 3, this gives us square root of 3 over 2. Sine of minus pi over 3 gives us minus square root of 3 over 2. And this is called an odd function. So if we had sine 2 pi over 3, 2 pi over 3 is the sine of pi minus a third pi. So if we draw our quadrant diagram, it would be pi is here, this is 0 degrees, pi over 3, or a third pi rather, would be here, or pi over 3, whichever you prefer. So this then is minus a half square root of 3 over 2. So the sine value is given by square root of 3 over 2. Sine of minus 2 pi over 3. This is the same as the sine of minus pi plus pi over 3. So if we draw our quadrant diagram, this is pi. So pi minus pi is here, and plus pi over 3 we would get from our unit circle we know that the values of the sine and the cosine are minus a half and minus square root of 3 over 2. So our sine value would be this one, which is minus square root of 3 over 2. So we'll look at cotangent of 10 pi over 6. We know that this is cotangent is cos over sine. So it'd be cos 10 pi over 6 over 7 10 pi over 6. Now 10 pi over 6 is the same as 2 pi minus pi over 3. So if we draw our diagram here, it'd be in this, the fourth quadrant, and this being pi over 3. X and y values are a half and square root of 3 over 2. Because we're in the fourth quadrant, this would be a minus. So now the cotangent is cos over sine. We know that this is cos, this is sine, x and y. So to work out cotangent, it becomes cos, which is a half, divided by sine, which is minus square root of 3 over 2. This is then a half times square root minus 2 over square root of 3. These cancelled, and we're left with minus 1 over square root of 3. If we have a tangent, we'll do that in the same way. Let's move this up a little bit. Say we had tangent 5 pi over 3. This is sine 5 pi over 3 divided by cos 5 pi over 3. Five pi over 3 is 2 pi minus pi over 3. If we draw our little quadrant diagram, it'll lie in the fourth quadrant, with this being pi over 3. Our values of sine and cosine are a half and minus square root of 3 over 2. So when we put our values into our tangent formula, we get minus, this is the sine value, minus 3 square root of 3 over 2 divided by a half, which is minus square root of 3.